Welcome, welcome to signal processing for communication for 5G with millimeter wave. So, today we will be covering the lecture number 9 for the wireless channel array tracing model part 2. Today we will explain more into the digital channel part. So, last week or last class we have explained more on the IR to FIR conversion of my channel, right. So, if you look at the last class note, you will see that the channel was actually an IR filter and we have finally converted to some sort of an FIR filter by a simple method of windowing. Okay. Windowing meaning you just discard the values which are of no importance to us, but that should be at the end. Windowing does not mean that in between there are 0, you just discard them. There will be 0, but it is just like a delay element kind of thing. So, we will talk more on that. So, things that we will be covering are the following: general bandwidth aspect of channel and transmitter data. So, we will be showing how exactly they will be related and what happens when one of them is greater, another one is smaller. So, that kind of conceptual aspect. Then I will be talking about frequency flat fading and frequency selective channels, and then some diagrammatic view of the frequency selective aspect. So, what exactly it means for it. For example, there will be a FIR filter, IR filter of the channel model, that will be. So, what does it mean? It means we have the channel. So, let us say, so I can now straight away think of it as like a system of linear equation, just it has the components, whatever delay components and the channel components we have. It is like a filter. So, when you have a filter, you have a lot of coefficients into it, right. So, each and every tap is as if like a coefficient for that filter. That is precisely what is there. So, now let us say this is the Lth tap, and let me just generalize it. So, instead of HL, if it is a filter, so obviously I can have some sort of a transfer function of it, right. If it is a system of linear equation, I can get a transfer function of it. So, this Hz is the Z transformation of that individual HL. So, what does it mean? I can say this is nothing but H0 will be there plus H1 Z inverse plus H2 Z inverse 2 plus dot dot dot. Say I have considered up to L number of taps, because beyond that I do not see any more taps coming up. Okay. So, it will be HL minus 1 Z to the power minus L minus 1. So, this is my actual tap. So, this is an Lth order FIR filter. It is an Lth order FIR filter. Okay. But note that though it has its order is L, it does not mean that each and every components or the coefficient within this filter of order L will be all non-zero. That is not guaranteed. Why? Because look at this, or look at kind of this diagram. Look at this diagram. Let us say I am in the second sampling. You will see that initially few taps will be non-zero, then again some value will be 0, again some non-zero, some will be 0, again non-zero, and finally it will be 0. So, that means between the coefficients, some of the coefficient can just vanish because of this non-existence of the original reflectors. If I sample it even more, probably I have to increase my order here, order of the filter is more, but you will see lot of 0 in between. Finally, of course, this part is 0, that is fine, but you may see that. So, in a conclusion, I can say that though its order is L, not every component, so these are all like a component. So, this we call it a taps, right, or channel coefficient if you think from a filter point of view. If you think from a plain filter point of view, they are all nothing but the coefficient of the filter. So, these are all the coefficients of the filter, or nothing but the tap, what usually I refer to taps. Now, even if its order is L, does not mean that all the H0 to HL minus 1 they will be non-zero. There is no guarantee. In between there will be lot of zeros. So, it may happen that just take an example. Let us say I am taking an example, say H0 Hz is equal to H0 plus let us say H3 z to the power minus 3 plus H7 z to the power minus 7. So, this is the filter. So, what are the coefficients? Does it mean that its coefficients, it has only 3 coefficients? No, it has actually 8 coefficients, just that some of them will be 0, because its order is 7. So, what does it mean? It means that probably H0 has a value, but H1 is 0, H2 is 0. So, this is H0, this is H1, this is H2, but H3 has some value. Then 4 is a 0, 5 is a 0, 6 is a 0, but H7 can have some values, and H8 if it exists, though we do not consider anything. So, after that every point is 0. So, this is how the tap is, this is how the tap looks like. So, never say that just because order is 7 and some of them are 0, it does not mean that those coefficients do not exist, just that it is 0, that is all, because it is in between. But of course, beyond the highest point everything else will be 0. So, this is a typical, typical channel examples where in between you can have a 0. Okay? This is one point. Let us do some more characterization of the channel part. Now, as we discussed last time, delay spread, right. Now, delay spread, what happens to the digital case? Because in digital the exact time difference between the reflectors as I perceive after the sampling may not be the same, right, because it is a uniform sampling. Right. So, now how do I define the delay spread there? Does the delay spread completely changes here? Well, tentatively, but delay spread is an inherent property. It is an inherent property of my channel things, right. So, they may not change, but rather I may not be able to find out exact the delay spread just looking at my samples, only if I do a higher sample, because only if it is a higher sample I can exactly somehow point out what is the spread of my what is the where the exact reflectors or scatterer they are presented, but unless I sample it very high speed it is slightly difficult. I think we have just explained it. So, the delay spread becomes some sort of a intrinsic property of my channel. So, even if I sample it, even if I sample after ADC, they become uniform, but that is okay. So, probably your tau 1 somewhere was here and tau 2 somewhere here, somewhere your tau 1 maybe say somewhere here or maybe somewhere here, maybe somewhere here your actual tau 1, and your last tau say tau say 3 was somewhere say somewhere here. So, does not mean that after digitization I will not get anything beyond tau 3. So, I may still get something, but it may die down quickly, it may die down quickly, it may die down quickly. So, the actual delay spread which we observe for the channel here say tau d, and the channel say for example, I observe my first step somewhere here and I observe at least last step here, and anything beyond that I do not get it. So, this is my tau d I would consider, because that is the delay between the first step and my second and the last step, and that is the definition. So, this is my tau d, but it is actually digital. I would say this is d, but it is digital, tau d of d I call it. Now, there is no guarantee that tau d and tau d d will be equal, but they are related. Okay. So, I cannot say they are equal, but I would say they are of the order. Naturally, there may be extra few sample they may come, obviously, because it is a sink, right, it depends on how you are sampling it. Okay. So, but there is a correlation. So, this is my RF analog exact tau d the delay spread give, this is after digitizations. Okay. So, they may not exactly match, but they are related. If this is in the order of say, I will just give an example 10 microsecond, you can't expect that this becomes 100 microsecond, that will never happen, obviously, right. If there is, if this is the last step physically and there is obviously a sink, so after 1 or 2 extra you may get it, 1 or 2 extra, not more than that, right. So, if this is, it will never be 10 microsecond, but I can't say how much it would be, but obviously it will be very close to that. So, probably it will be 11 microsecond, something like that, or maybe 9 microsecond, something like that. So, it may not be equal, but it will not be of that huge order, or if this is say 1 microsecond, you can't expect that this becomes 1 millisecond. Okay. It may become 1 millisecond provided you lower your threshold, okay, and probably that can drive what should be my threshold such that it really matches my taps here. So, you can't expect this kind of things. So, this is my delay spread definition. So, I will not consider from now, it depends where exactly you can think of your delay spread. Now, as you notice in practical sense, when you have a modem, it is a digital modem, right, this is difficult to find. Because how? The reason is that everything you observe a system only by sampling, right. You do not do any processing at the analog or RF, right. So, there is nothing called analog processing, because had I done an analog processing where I can precisely see where my taps are, it is easy to find out, but I do not do anything in analog or RF, I do everything in the digital side. So, which means I have to pass through the ADC. Moment I pass through the ADC, it means the concept of tau d does not exist for me. What exists for me is more of this one, digital, digital delay spread, that matters to me. Okay. So, this is one definition, that how exactly I will consider, but as we notice they are of the same order tentatively. Okay. So, we have learned delay spread. Next, some of the parameters that I would like to have it is the following. So, what about the bandwidth? Bandwidth of what? Bandwidth of the channel, because it is a system of linear equation, it is like a filter, right. So, if you say filter, filter has a bandwidth, either infinite bandwidth or some finite bandwidth, everything comes into picture. Whatever parameters you can have it in the filter, everything will be there. It may have a ripples, pass band ripple, stop band ripple, it may have a delay characteristic, it will have a phase characteristic, it will have a bandwidth concept, roll off factor, whatever is there in the filter, it will also have the same thing. So, let us characterize that, right. So, now we have a 2 point. One point is that, so this is my antenna where I have done a transmission, but as you notice I am viewing the whole system from a digital side. So, I will not draw ST here. What should I draw here? SBN, because I am viewing my system SBM or SBN, that is okay. You can write N also if somebody is not comfortable with this parameter, SBN, some digital part, because the whole analog RF everything I push it as a channel, that is what my channel. So, everything, so beyond this point I have DAC, I have different filters, modulator, power amplifier, all damn things I push it as a channel. And when I have a receiver side, I have that that LNA, demodulator, bunch of filters, and finally you have the ADC. So, here I am standing, right. So, I have YBN. So, my view of channel is from here to here. This is whole my channel. Air is not just the only part, everything else is my channel. Okay. So, my view is that as if like I am sending SBN and I am viewing, or I am getting, I am receiving YBN. So, my channel was HZ. So, finite impulse response, we have discussed it. So, this is my SBN, this is my YBN, right. So, what is this? How do I estimate my spectrum? If this is the finite impulse response, it is a Z transformation. If I know the taps, I can easily get it. Just replace Z equal to e to the power j omega. Fine. So, if you have a Z, I can easily convert it to H of omega. How do I convert? I just replace. This was L, right. This is, if it is a Z transformation. Now, this will be converted, this will be replaced. This is what it will be. Now, L equal to 0 to now I have created a finite impulse response just by doing some sort of a thresholding. So, this is my channel spectrum. Now, this is the h omega. Now, you plot it, you plot mod of h omega, you will get some spectrum whatever it is. So, it will be pi to minus pi, you will have some spectrum that can happen. Okay. Let us understand more on that. Now, you have a problem. What is the problem? Problem is that you already have one spectrum from your transmitter side. Why? Because you have a DAC. So, DAC has a sampling rate. So, which means that you have certain power and certain bandwidth of your transmitted signal that get transmitted through this channel, and finally, you get received, you are receiving that. So, the effective bandwidth will be a combination of your channel as well as your input data. Okay. So, can I say if I take y b omega, I can naturally see it will be h omega and s b omega. It is a system of linear equation, static system. I am not creating any time varying system, otherwise it will not work. If it is a time varying, this does not work out. Okay. If it is a static system, this works out pretty well. We will explain what happens when it is a time varying, and that is your Doppler constant. So, this is what it is. So, what does it mean? It means that it depends on this bandwidth and this bandwidth, based on that this y b omega comes. So, let us say this gentleman has a bandwidth of B s, it's a baseband bandwidth, and this gentleman has a bandwidth of, say, let us say B h, that is the baseband bandwidth of my channel, because everything is a baseband for me, it is a digital baseband for me. Okay. What should be the bandwidth here? It depends who is bigger, all right. If B h is greater than B s, what happens? It means your channel bandwidth is more than your data bandwidth. What happens? It means this is a scenario. Now, we need to understand the impact of such kind of scenarios. Let us say you have this B h. So, this is your B h, okay, and this is more or less your data bandwidth. Okay. So, can I say my B, let us say the bandwidth at the output or received side is B y. So, can I say B y will be nothing but B s, it will be equal to B s, obviously, right, because B h will pass on everything, or it will be B h if B h is less than. This is a very standard filtering concept, nothing great about that. But let us understand what is the impact for case number 1, what is the impact for case number 2. What exactly it means? That your channel bandwidth is greater than your transmission bandwidth and channel bandwidth is less than your transmission bandwidth. What is the impact of it? Naturally, if you see that in the case number 1, when the channel bandwidth is more than your B s, what does it mean? It passes most of the component of your transmission system. Obviously, there may be phase distortion, but at least the components go through with some distortion in the amplitude. But look at the second case. Second case, channel bandwidth is lesser than your system bandwidth. So, it discards some of the components of your data, which means it degrades the quality a lot, right. Now, let us understand what does it translate to in our system when the B h is less than your B s. That means, your transmission bandwidth is much greater than your channel bandwidth. So, channel bandwidth is smaller. Okay. Okay, so, let us understand that part. What happens? What is these two cases? So, first case is your data bandwidth or your rather channel bandwidth is much greater than your data bandwidth. So, your total output bandwidth, your BH or your B of y will be equal to your B of s. It passes on each and every signal, right. So, what does it mean in a very simple sense? That means, I am seeing that whatever I have transmitted, barring the phase part, phase distortion part, each and every frequency component get passed out. Got my point? What I am saying is, when By is equal to Bs, what does it mean? It means that each and every frequency component present in my transmission signal, they all pass through. When can it happen? What should be the channel or rather than the filter such that it passes on everything? So, can I say, if I plot, say for example, let us say this is my pi to minus pi. I have adjusted my sampling in such a way that within pi to minus pi, I fully can see my Bs. So, this is my Fs by 2, sampling Fs by 2 at the transmitter side. So, I have adjusted my sampling rate such that it completely occupies the input bandwidth part. Whatever input I have sent, the same spectrum it just fits into pi to minus pi. Let us assume that I am doing that kind of sampling. So, what does it mean? It means that the whole Bs, that whole transmission bandwidth is exactly fits in my pi to minus pi without any distortion, without any component lost. Nothing will be happening. When that can happen? That when whatever I transmit, everything I get back. Can I say if a channel is something like that? So, let us say I have a channel which is just say H0 plus H1 Z inverse, or I have another channel, just one tap. Now, let us understand, out of the two cases, which case we pass on or pass each and every component of my data, transmitted data, provided within pi to minus pi, I exactly fit my input data. That means, either the filter is as if like this, original channel filter, then only it can happen, no, it can happen, right? Then it can happen, it passes everything because it exactly fits it. Okay, this is the worst case scenarios, nothing more than that. Or it can happen that I am sampling at a higher rate, so that I can view the data. So, this data is dotted data, this is my higher sampling rate, my channel bandwidth is larger to it. So, with respect to my transmission window, if I just do not look at anything beyond my transmission window, what does it mean? I will see that across my transmission window, the channel has presence of frequencies. So, the channel does not give any distortion or does not cut off any distortion as long as my transmission bandwidth is wherever I am transmitting it. That means, if I just transmit 10 megahertz and I do not look anything beyond that, because that is my transmission bandwidth. So, what does it mean? It is as if like within my transmission bandwidth, my channel is just like it is present everywhere, it is omnipresent. What does it mean? It is as if like my channel is an all pass filter, correct? Then only it can happen. So, which means that if my pi to minus pi, within it my channel just fits, my data just fits, and I am saying that after transmission my data has no distortion. It simply means that within my window of view, if it is just exactly tight, my complete 10 megahertz, that is my transmission bandwidth, is as if like my channel is an all pass filter. It is an all pass filter, right? If it is an all pass filter, it just passes on each and every component of yours of your transmission bandwidth. So which means this is one scenario where I can think the channel just passes off everything. So, what is the bandwidth of such signal? Bandwidth is infinite, because this is just one tap, right? One tap. What is the bandwidth? One tap meaning it is just one impulse. Bandwidth is infinite, right? If it is just one tap, this is your H0. So, what is the bandwidth? Bandwidth will be infinite bandwidth. It is not infinite bandwidth. It simply says that within my viewing window, can a tap have an infinite bandwidth? Virtually impossible. You can't have it. You cannot have an infinite bandwidth of the channel. It all depends on how you sample it. Okay. So, which means that if the channel is just like some sort of a multiplier or just a gain increment or decrement, of course gain will decrease, the channel is as if like it will viewed as a infinite bandwidth channel. It simply means that the window I am looking for, the channel exists everywhere in that spectrum. The window I am looking for, the channel exists in that window. So, it is like channel just has a like one, it is like a all pass filter. So, such kind of channels, if the channel is just a just has just one tap, it does not create any distortion in your system. In that case, it just passes off everything, and it is as if like I am going through just like an all pass filter. So, such kind of channel I call it frequency flat fading channel. Frequency flat fading, that means it does not introduce any frequency suppression on your input signal, it is just make everything goes through. It is a frequency flat fading channel. But what happens when my channel is this kind of channel, at least it has more than one tap? What will happen to it? What will happen to that? It no longer be a frequency flat fading, because it's now it may cut down some of the taps, is some of the frequencies, not taps, some of the frequencies of your data. So, it simply means that within my viewing window I am seeing some of the component just get, that means the bandwidth of this channel will be much lesser than the bandwidth of my transmission. So, what is the impact of it? Then only I can see some of the points or some of the data can be discarded. So, what it means in the time domain? So, if I have a bandwidth of a signal, this is my say transmission bandwidth, and after I do a reception, it gets shortened. The bandwidth is shorter. What is the time domain impact? Time domain impact is that you will naturally see some sort of an aliasing, because some of the components are lost, right? Some of the components are lost. So, what is the impact of it? You will see some sort of a aliasing effect on that, because only aliasing can effectively kill some of the some of the data that you are transmitting it. So, when you lose some of the components after transmission, it simply means that you may have some sort of aliasing in your time domain. So, that is reflected when your channel is having more than one tap. So, it is cutting off some of the frequencies. So, it is as if like your transmission bandwidth, what your bandwidth of interest, your actual bandwidth of your channel is shorter than that. So, some component is just cut down. So, it simply means that the channel or the received data is having aliasing. Look at this. If you have this kind of filter, what does it mean? What is the YB? YBN is H0 x of n plus H1 x of n minus, not x. What is this? What is this component? That is aliased. It will be creating a time domain aliasing, right. So, this is your time domain aliasing. Okay. So, this is also called ISI, intersymbol interference. because that means the previous data is now get an aliasing in my present data. So, it kills, it simply kills some of the present component, and that is precisely what is happening here. So, which means that if the bandwidth of the channel is less than your Bs, the impact is that you will see this time domain aliasing or ISI. That means, some of the previous data will now come into your present data, and that is kind of an interference. Okay. So, now this is your such scenarios is called frequency selective. Frequency selective fading. So, one is a frequency flat fading, it is as if like a all pass filter, as if like all pass filter, just one tap. More than one tap meaning the bandwidth is tentatively lower than your system bandwidth. So, it sees some sort of a interference, time domain interference that will come into picture, because you have cut down some of the frequencies, right. So, it will create some sort of a time domain aliasing or time domain interference, and this kind of channel is called a frequency selective channel. So, when you say frequency selective channel, it simply means you have more than one taps. So, today we will stop it here, we go more details into the next class. Okay. Yeah. And the reference will be same as what we have said in the earlier class, Fundamental of Wireless Communication by David C. and P. Vishwanathan. Thank you.